express a certain things which is moving with that frame. Okay, and if you want to find out the resultant speed of that moving what one that thing happen in the moving frame, okay, to the stationary frame, then we just express as the what simply the velocity addition rule. Okay, that's the simple classical things that we generally do. But what is happening when the certain things which moves with a speed, okay, comparable to the speed of light? So your classical relation is not been true over here, okay, and it not verifies the what we say the postulates of the special theory of relativity, in which we say that nothing will be a faster than the speed of light. Okay, so whatever be the speed, that is a maximum to the speed of light. Okay, even the photon which moves, okay, two photons are moving one relative to other, you cannot do c minus c or c plus c over there. Okay, the resultant speed is the speed with that photon, that's electromagnetic wave, okay, moving with a constant speed is what, that c. Okay, and that's the c remains to be a c, not greater or smaller than that. Okay, so every object or moving thing that has to be lesser or to the maximum c that we have. So here when we are doing the classical addition, that is not that is discarded, and I will take that problem also in the last of this section. I will just give you today the how this velocity addition formula relativistically get proved, okay, and how this formula is related to our I mean to say that's confirmed from the what, the Lorentz transformations equations. So here I'm talking about the special relativistic postulate that the speed of light in a free space has the what, the same value for all observer regardless of their relative motion. Okay, and this is what we always a common sense that the Galilean transformation that we generally study and that has not been given you the equation. So equation what I'm talking to you here, the relativistic equation, that going to be a change because of the velocity that is velocity addition rule that given by the Galilean transformation is not obeying over here. Okay, suppose you are throwing a ball forward, I mean to say with a certain speed 10 meter per second, and from a car, and which is also moving with the 30 meter per second. Okay, so ball speed relative to the road, that means you are the observer on the road. Okay, and that what stationary will be a simply you are doing with 10 plus 30, that's a 40 meter per second. Okay, so stationary observer observes that ball which is moving in a same direction, and the car is moving along the same direction. That car's speed is 30 meter per second and ball speed is 10 meter per second. So the resultant ball speed because of that car is moving will be a what, 40 meter per second with respect to the road. Okay, so the sum of the two speed that we have generally do with the Galilean things, and the classically we are doing this addition law. Okay, but if we switch the car's headlights, and now its speed is v. Okay, and the reasoning we need to do here with the light. Okay, so can we apply the same reasoning over here? Suppose the that car's headlights, okay, that emits the light over there, and they are emitting a light from the that frame of reference, means car's frame of reference, which is a moving frame, that's what it's s prime. Okay, in the same direction as the direction of its motion, that's what the motion of that with respect to the stationary frame, that is what your road. So the speed of the, that means the direction of motion means speed of the what we say the light which is relative to the road will be how much? It is the heads, that's the speed already have the light in a what we say with which it is moving with the speed of light, and the frame which is moving with the what, the velocity. So c plus v, that is the value you will have. Okay, as a resultant value as the what you just say that c prime, or you say whatever be the velocity with which we measured the value in a stationary frame will be the what, the velocity of light plus the velocity with which that frame is moving. Okay, so that c plus v is an addition formula, but remember that your c prime here, it's supposed to be a value you are getting. Okay, that what you have the c plus v. Okay, but which is not true. Okay, and here it is not something like you are doing addition or subtracting. C is always be a c. That is what it violates the postulate, and that's the postulates of the what, the first postulate of the special theory of relativity, and speed of light, which is remains to be a constant over here. Okay, so what to need to do here for this correction? Okay, and we need to use the corrected transformation, that are the Lorentz transformations. Okay, and those transformation we need to correct the velocity addition rule. Okay, velocity and addition formula. So there should be a correction. The classical relation that the Galilean talk about, the c as a c plus v it becomes, so that need to be a corrected. So what are the Lorentz transformations equation do you have? You have those equations with you. Okay, those the moving frame. Okay, their position with respect to the stationary one, with the velocity with which it is moving v in a real time t, that you express. There is no changes along the perpendicular directions. You are having y and y prime that remains same, z and z prime remains same, but there will be a change in the time because of the space changes, because space is changing, time is going to be a change, and this is the relation. So you have a relations of those Lorentz transformations in a what, the moving frame, and the inverse Lorentz transformation equation that you have, that is in the what, the stationary frame. Okay, that you just express xyz in terms of xyz and t in terms of y x prime y prime z prime and corresponding t prime over there. Okay, so these transformations equation that we need to use to write down the general formula or the velocity addition formula that we can derive over here from this, using this Lorentz transformation equation. How we can do, just be a next slide. Suppose something is moving, I mean to say, so you will have the what, the just we have a case of what, the train. Okay, which is a moving with respect to the what, the road. Okay, and you have a passenger there, and that passenger is moving in the train with certain velocity v. So this is an example we always talk about. Okay, so you have a one frame, always be a stationary frame, and there is a moving frame. Okay, that is a s prime frame, which moves with a certain velocity v with respect to the what, this stationary frame. That is the general understanding we have. So we have over here the s prime, that's the moving frame, and we have a constant frame, that's the s frame, that's a rest frame. Now we have a certain thing, that's the what, there is a certain things which is moving with respect to this moving frame, that's what, the s prime frame. Okay, and we need to find out their velocity. So here here we need to consider there are certain things moving in along the what, the positive x direction. Okay, now moving relative to what, this stationary frame, and that is happening the things in the s prime frame you have. Okay, now observe which s measures its three velocity component. So you will have a real velocity component, you can calculate the rate at which the what, the position changes. So vx is a what, dx by dt. Okay, that's the equation you have. Another equation on the y changes will be a what, dy by dt. Okay, and the z direction velocity, if you want to calculate, okay, the rate at which the first order position changes, that's you have a dz by dt. Okay, these are the what, the velocity components of vx, vy, vz are the corresponding components of the velocities along the three directions you have. That's what, the x, y and z, that's the real velocities, you can write it. Okay, the corresponding velocities in the what, the x prime, y prime and z prime, that you can calculate it, and their values you can easily calculate it by just taking the what, the position changes with the what, the time changes they have. So that's what you have, the corresponding time frame over here, the t prime, and the real time you have a t over there. Okay, so these are the things happening and I mean to say you will have to find out the velocity in the x prime frame. I mean to say the s prime frame. So corresponding x component is a what? V suffix x. Okay, and that represents prime. So V prime x represent the x component of the velocity in the s prime frame, that you can calculate it by just taking the differentiation of the d by dt prime. Okay, remember here we need to differentiate, okay, with respect to the t prime. Okay, so d by dt prime of what, which position, x prime. Similarly, we can do the v pi prime, that is what the first order differentiation of this d by dt prime with respect to the, I mean to say d by dt prime with y prime over there. Okay, and similarly you will have the vz prime, that you can calculate it by just differentiating dz prime with respect to the dt prime. Hope you understand. These are the all three components we calculated of x, y, z primes, but their positions we just represent, I mean to say their velocities we need to represent by v prime over there. So vx prime represent the x component, vy prime represent y component, and z component of this moving frame. Okay, that's the s prime frame that you have. So now by differentiating, you will have to use the inverse Lorentz transformation equation, because we need to calculate the real values. You know that these are the x, y, and z. These are the real calculations you can do, okay, by doing the inverse Lorentz transformation. So this on the right hand side, this box you just represent, these are the inverse Lorentz transformations. Inverse Lorentz transformations. Okay, you just have to have consider the, okay, just xyz real time xyz t in terms of what, moving one. Okay, that will be used to have the real inverse Lorentz transformations equation, and you have the xyz t corresponding. So what is this dx? What you do, you just to have the differentiate, okay, the first order differentiation of this dx, okay, with respect to the what, t over there. How can you do that? So you just dx, take a differentiation, and take a differentiation of this dt. So you will get a dx by dt. That's what. So that we will do later. First we will do the differentiation of the dx. So we'll just do the differentiation over here of this x dash x prime, you say, and vt prime plus vt prime. So here we do the differentiation, that's the dx prime, okay, and the corresponding differentiation of the corresponding t will be a dt prime. Okay, so you will have a relation becomes a dx is equal to dx prime plus v dt prime divided by square root of 1 minus v square by c square. Hope you are understand. That is what we have the equation, that what certain thing which is moving in the what, the positive x direction. So there will be no changes along the y and z. So you will write that dy prime as a dy prime and dz prime as a dz prime. Okay, I say dz is equal to dy, dz is equal to dz prime, and dy is equal to dy prime. And you are differentiation of the what, dt. So take a equation of what t you have. Okay, you take a differentiation of this equation, okay, and differentiation of this value. I'm talking about the value which is in the t prime plus v by c square, which is multiplied by x prime. That you have equation of the what, time equation you have. So Lorentz transformation time equation, you need to take just differentiation. So dt you just express as a dt prime, and dx prime becomes a, when you differentiate, it becomes a dx prime. Okay, this is the constant which are remains to be a same. Velocity with which that frame is moving as a constant. Speed of light which is a constant, which are remains as it is. Only the prime coordinates which are changing. So you will have a dt prime over here, and you will have the corresponding sorry, over here it should be a dx over here. I'm sorry, here it should be a dx prime. Okay, so dt prime is equal to v dx prime divided by c square square root of 1 minus v square by c square. Now you have a dx, you have a dt. Now what to do? You have to just take a ratio. I mean to say the first order differentiation, that is dx by dt, that gives me a velocity vx. Okay, so you just do these calculations here, just put the value of dx over here as dx prime plus v dt prime, and you put the value of dt as what, this equation which tells you a value of what, dt prime plus v dx prime by c square. Hope you are understanding. These are the simple mathematics we are doing, and we are just finding out the velocity in the x component. So you just do the dx by dt, okay? And you can calculate the values now, dx prime by dt prime plus v, and you are finding the value of 1 plus by v square dx prime by dt prime. You just divide, I mean to say, just common out the v. So here it to be dx prime by dt, okay? So dx prime by dt means you divide it by dt prime. So you just divide it by dt prime over here, and when you divide it by dt prime on the numerator and denominator, okay, if you are dividing dt prime, that is the what, the numerator and denominator by the dt prime, you can easily get this dx prime by dt prime over here plus v, that dt prime get cancelled, and you have a dx by dx, dt prime by dt prime becomes a 1 over here, and 1 plus v by c square, that is a dx prime by dt prime. Hope you understand the mathematics arrangement we have done over here, just by dividing numerator and denominator by the dt prime. Okay, so the formula which ultimately becomes the velocity vx, okay, you can write it, sorry, you can write it over here, this dx by dt prime, that is the what, the velocity in the, that's a component of the vx prime component, okay? And this is the velocity v, and this gives me a velocity component here also in the prime. So how's my equation become? So I'm writing here the equation for the vx. Okay, so vx is equal to, this becomes a what, this becomes a v prime, okay, here x component plus v divided by the 1 plus v by c square, v by c square, that's a constant, and the what, dx by dt prime, which is nothing but again the along the x component, is which is nothing but a vx prime over there. Hope you understand how we can get. So you will have the real velocity, that is a vx, okay, that is equals to the what, the velocity with which that thing is moving, okay, in the s prime frame will be a vx prime plus v plus divided by 1 plus v by c square into vx prime. So it is like that. If you have a certain, I mean to say, you have, just consider an example of a train, okay, but this is not a classical thing. You need to consider a certain phenomenon, okay, where the what, the particle is moving with the comparable to the speed of the light, okay. So then we can use these relations over there, and actually you can get the resultant formula of the what, the things happening. So how's that relation ultimately get it? I will take one problem. You will understand by that problem how this relation, which now you have a velocity, okay, in the x direction, which is you can calculate it as a what, vx prime, and the velocity with which that frame is moving with v is not simply a vx plus v over there. It will be a vx prime plus v divided by this component, okay, 1 plus v into vx prime by c square, okay. So your classical, or you say the relativistic addition rule, that been corrected by with the help of the Lorentz transformation equations, and you have an equation of this relativistic transformation becomes, okay, the equation in the what, when the certain thing is moving in the positive x directions, then you have to observe what the speed relative to the observer, which is a stationary, okay, their speed you can calculate it with the help of this particular formula. Now the things that I say, there will be the corresponding things is happening along the y direction and z direction, okay. This is the velocity. Remember, the velocity, it is not like of just there is a no change in the position, but the position is going to be a change with respect to the time. So your equation that I want to say, that dy prime by dt prime, okay, you have to use it over here, and vz prime is equal to dz prime by dt, that you have to use it over here, okay. So your equations of dt prime, which is you need to put it over here when you are calculating the value of dz. Similarly, you need to put it in the value of dy when you are finding the what? I mean to say vy. It is a dy prime by dt prime. Okay. And similarly, you need to find the velocity along the z direction. You need to do a differentiation of dz prime with respect to the dz prime with respect to the dt prime. So hope you understand the velocities component when you are doing. You need to take care of putting the value of dt prime over there. Okay. So dt prime equations you have always with this equation. Okay. So when you are finding the relativistic addition rule, okay, the velocity component y and z component also going to be a change, and their values you need to calculate it. You can observe, okay, this is not simply a vy is equal to vy prime or vz equal to vz prime. Your equations is going to be a change because of the time is going to be a change over there. Okay, so your equations vy is vy prime times the square root of 1 minus v square by c square divided by 1 plus v prime vx prime by c square, and vz you can prove and you can get it, okay, by just doing the mathematical things over there. Okay, so hope you understand these are the three relations that we got it. The relativistic velocity transformation that we did it with the help of the Lorentz transformation equations, and these equations talks about the velocity components of these things. Okay, there are certain things which is doing in that moving frame, and if you want to observe that things with respect to the stationary one observer, their velocities, okay, can be calculated with the help of these three components, okay, vx, vy and vz. Hope you understand these are the three relations. I think there is no question because I explained about how to derive these particular relations. Okay, mathematics playing a role over here, and we got these ultimate three equations. We called it as a relativistic velocity transformations. Okay, now the things are very simple, and now it not violates the what we say the relativistic law, or you say the relativistic postulate given by the Einstein first postulate. Your velocity of speed of light which is remains to be a same. That's what we say, that if the light is emitting in the what the moving frame, if the light is moving in the emitting frame, I mean it's a moving frame and it is moving, I always say that the speed of light, okay, with which is moving, and that frame is moving with the velocity v. So your vx prime is a c over there. Okay, you just add value of vx prime as a c plus v, and the denominator you have the what? In the numerator you have a c plus v, in the denominator 1 plus v times vx prime. Now vx prime is your c, so vc divided by c square. So you just do now the v by c over here, and you just do the c, common it out here, c plus v. Here also you just common it out c, so you will have the c plus v. Okay, so you will have the simple relation which is coming out, c plus v is cancelled with the c plus observer on the road will see the speed of light is the same as the speed of light. Okay, it will not the adding the velocity, that it not becomes a c prime as a c plus v. Now your c prime, you simply say that with which that c is moving as a what? Simply a c. Or you say that the velocity with which that thing is observing. So don't confuse. Okay, here the x component I'm talking. Okay, don't say c prime. Okay, vx as a c over there. Okay, so that's what you are not violating the postulate of the special theory of relativity. So c is remaining, say c. So this is the corrected transformation, and these are the values, are the corrected values. You got it from the what? The Lorentz transformation equations. You ultimately got the relation of velocity addition formula that you derived by using the Lorentz transformation equation. Hope you understand. So then I can take a problem on that. If you have any question, please ask right now to me. Do you have any questions? So please ask me. Are you getting what I'm going to explain today? This is the velocity addition formula that we are going to derive using the Lorentz transformation, which not violating the relativistic law. That what violating by the Galilean transformations. Okay. So here, if you want to take any problem, just like, okay, if you want to consider a spacecraft, okay, that name is Alpha over there, and that spacecraft is moving with the 0.9 c, means 90% of the speed of light. That is we called as 0.9 c with respect to the Earth, okay, that's what you have Earth, and you launch a satellite. That satellite, sorry, spacecraft, and spacecraft is a moving with the speed of light. Now, this spacecraft beta there, okay, is also there, and that spacecraft beta is to pass alpha that spacecraft at a speed of 0.5 c in the same direction. So this is like the same problem if you have a train which is moving with a certain speed with respect to the road, and there is also some passenger which is moving with respect to the train. So that is what you have. What there is another spacecraft beta which is moving in the same direction as that of the alpha spacecraft, and that relative speed which is mentioned over there is a 0.5 c. Okay, 0.5. So what the speed of that beta spacecraft you have with respect to the stationary Earth that you have? I mean to say, when the observer is on the surface of the Earth, which can looks the what the corresponding beta speed, okay, with respect to the what the one. So here, when we are talking about that, the same similar analogy, okay, what the velocity of that Galilean transformation. So if you use the Galilean transformation, you will have the velocity with which that relatively that one alpha is moving with respect to the 0.9 c, and then relative speed is a 0.5 c. So Galilean transformation, which gives you answer, zero point 0.9 plus 0.5 is 1.4 c. Okay, so this is the answer which is given by the Galilean thing. Okay, but which is greater than the what you are getting the value 1.4 c, which is greater than the speed of light, and that is violating your postulate of the special theory of relativity. So you need to correct, you need to use your law of velocity of addition formula, that is to be corrected by the Einstein's velocity addition rule and law, and that we need to correct it over here. So we need to consider the velocity with which that frame is moving with the 0.9 c, and there is another spacecraft which is moving with the 0.5 c with the alpha spacecraft, okay, 0.5 c. So we need to add that value as a 0.5 c Vx prime, okay, that is a 0.5 c over here, and the 0.9 c is the what the velocity which that frame is moving is the velocity v over there, and we need to add those values on the numerator, zero point 0.5 and 0.9 times c, remember, and divided by this factor 1 plus v into vx prime divided by c square. So 1 plus 0.9 c multiplied by 0.5 c divided by c square. So this c and this c is cancelling with this c square, and you will get a value of what? The resultant value you are getting is a 0.97 c, and which is a less than the what the c you have. So remember, this is the correction, that is what you have. The correct value you can observe now, or you can calculate it, that the beta that is moving, okay, with the surface of the Earth, or with respect to the stationary Earth, or the observer on the Earth sees that beta spacecraft moving with the what value? 0.97 c, which is the correct one. Okay, so here it is necessary to go to less than 10% faster than the spacecraft traveling at a 0.9 c in order to pass it relatively at speed of 0.5 c. So that's the logical things. Okay, here if you want to have the relative speed between the what that space craft you have alpha and beta, their relative speed should be a 0.5 c, though there must be a two, okay, the another spacecraft, okay, that has to be a move 10% faster than the what, that's what the beta has speed greater than the alpha you have, okay, but that's the speeds you are measuring with respect to the earth, okay. So hope you are understanding this velocity addition rule, that velocity addition rule or velocity addition formula, that you can use it over here for calculating the relative velocities of the object, okay, or bodies or the things which are moving, okay, in a certain frames, okay, which are moving in a certain moving frame, you say, okay. So hope you understand this problem, and I request you people to go for the references for this book is just two books I am using over here. As you always, we are using the author Bizer. I'm taking the reference of the author Bizer and also the book of Resnick. You can observe for doing these things. Okay. There is another way, another approach of deriving this velocity addition formula. You can do it there also. Okay, with the help of this particular things. I'm not going to take again repetition of what we have doing, but you can just take a reference of that particular book and just see that how the formula is been derived over here. Okay, this is a relativistic addition formula. Okay, so classical, that's Galilean velocity addition theorem being corrected over here and by special relativity with the help of the Lorentz transformation you have. So can you people read this problem and try to answer with this relativistic addition law that's just been used over here? You just have to read, any one of you, just read this problem. Are you hearing me? Can you, any one of you just read the problem on the screen?
Two electrons are ejected in opposite directions from radioactive atoms in a sample of radioactive material at rest in the laboratory. Each electron has a speed 0.67 c as measured by a laboratory observer. What is the speed of one electron as measured from the other according to the classical velocity addition theorem?
So can you anyone of please try this classical and then we will do the relativistic addition. Okay. So what is the classical addition? Look at this, is the two frames which are moving in the opposite direction, two electrons. Okay, so you have the resultant velocity. You always write with the help of the just equation. I'm just you have over here the resultant velocities. Okay, just we consider that the example of the train and passenger. Okay, so always a classical rule. We always a train is moving with a certain velocity u prime with respect to the, I mean to say, sorry, passenger is moving with respect to the train and train is moving with respect to the ground. Okay, that's the what you have. But here in the example, we have to find out how much is the passenger velocity with respect to the ground. So you just do the vector sum of the two velocities. Okay, because this is the same direction with which that. So u is the what you say the passenger velocity with respect to the ground. Okay, u prime is the velocity of train with respect to the what? Sorry, train velocity with respect to the ground, and v is the velocity of this passenger with respect to the train. So you have the simple classical way is what the u is equal to u prime v. So suppose you have the train is moving with the 30 meter per second and the passenger is moving with the 10 meter per second. So you just calculate. So generally meter per second we calculate, but generally kilometer per hour. Suppose you have. But this is the what the resultant velocity. You can write it as u is equal to addition of these two things. So similarly, this example you can observe over here for the two electrons which are ejected in the opposite direction, okay, and their velocity, if you want to calculate it, Okay, so what you will do, this addition, this minus, this is in the same direction. Okay, so ux, that means what, the velocity of that electron with respect to the, what we say that, the laboratory, okay, that you observed as a measured by the laboratory observer is what, 0.67 and 0.67. So you will have, just consider one electron in the S frame, that is what, the laboratory frame, and you have the another S prime frame which is a moving frame. Okay, in that electron you have, but that frame is moving with a certain speed. That means what, in S prime frame the other electrons frame will be a what, 0.76 c. So you will feel like that the electron is a, with the velocity is a 0.76 c, and that frame is moving with the 0.67 c. So you will just add these two value, you will get the classically the value which comes out to be a what, 1.34 c. Again it's violating the what, the postulate, I mean to say the relativistic addition, a relativistic law or a relativistic postulate given by the Einstein. So correction, so that correction we need to do with the help of the what, the relativistic addition law. Okay, here, so here we need to found here the two electrons that are leaving a radioactivity sample in opposite direction, and they each have the speed c, 0.76 c speed, and they are classically have this velocity 1.34 c. That's what we just calculated. We need to calculate the relativistic velocity observed. Okay, what the relativistic velocity they have, these two electrons. Okay, so here we need to consider electron in S frame, that's the laboratory frame you have, and that the S prime, which is the moving frame, that another electron you have, and that is moving with the what, the 0.76 c. So you will have the electron speed with respect to that moving frame is a 0.6 c, and itself is a frame is moving with the what, 0.67 c. So remember that's the value you have to consider ux, u prime, that's a 0.67 c, and the frame which is moving, that's a 0.67 c. So here you want to do 0.67, 0.67 on the numerator one, and the denominator you will always have the what, this factor 1 plus u prime by v by c square. So don't consider here the x and y and z, just we consider that in a one direction. So we are just talking about the what, the resultant one. So you can ask me, sir, that time it was a vx, now why you are writing u over here? It's just for the understanding. Okay, the one component over here, the resultant component. Okay, so such as we are considering the x direction, only x direction, you can write over here the u suffix x also, but here you want to write that time also u suffix x prime that time. Okay, so it's not been the, just you have to remember the relative addition law is what, the it always be expressed as what, the ux is equal to u prime plus v divided by 1 plus u prime times v divided by c square. Hope you understand. And I'll just put it this value and calculate the value, and that value comes out to be a what, less than the speed of light, which is a correct one. Okay, so speed of an electron relative to the what we say should be less than the speed of light, and which is a corrected value which comes out to be over here the 0.92 c over here, 92% of the speed of light. That's the what the electron you can observe with the what, the laboratory frame you have or stationary frame you have. Any questions?
Sir,
No.
with respect to that laboratory frame, if we
Uh-huh.
increase speed of electrons in opposite
Yeah.
direction
Yes.
from 6.7 to 0.7, 0.8, 0.9,
Correct.
and then calculate the speed with respect to each other, then
You mean
that
to say,
you
their velocities are not uniform, they are changing.
no,
Yeah.
we do multiple experiments.
Okay, okay. Yeah, yes. You can do that. Yes, no problem. I mean to say, both the time you want to change the velocity, so both the times, I mean to say, next time you want to take those velocity values. Okay.
Yes.
So, okay,
Yes.
yes. You can do that. Yes, correct.
Then each time you will decrease.
U resultant. I mean to say ux. I mean to say
Yes.
What? Yes. So your values are goes on increasing. Resultant value goes on decreasing. Correct.
Means as that electron
You mean to say here instead of saying now instead of 0.67, suppose you have a 0.76 values. Okay, 76 or zero point 0.8 C you are just taking. So 0.8, 0.8 on the numerator and here 1 plus 0.8 whole square. So 0.8 is a 0.8 means 0.64. So 1.64 you have over here. And over here 0.8, 1.6. 1.6 divided by 1.64. How much value it comes? Just 1.8 divided by 1.6. Correct, no? वन पॉइंट सिक्स फोर हाँ सो किती येत आहे व्हॅल्यू किती येत आहे
0.9 something.
हा म्हणजे कंपॅरेटिव्हली दोन्ही जर आपण हे केलं म्हणजे सपोज यू हॅव द बोथ द थिंग सो कंपॅरेटिव्हली द रेशो आय एम टॉकिंग अबाउट ओके वॉट एव्हर सपोज यू आर इन्क्रीजिंग द स्पीड सो resultant speed may be a less than but that not too much 0.91 0.9 so that proportion 90% is still maintained okay so that's a enormous speed suppose you have to have these classical things I'm sorry relativistic thing at least you need to have the velocity greater than the 0.5 c then you can do the values correctly I mean to say those resultant relative values are 0.5 c so 10% increment may be there in the next one okay like that we do it in earlier problem also so what's your question
Means
suppose you have
just,
so
but
you are up
just
you
I
are
was asking that what is the nature of u that we calculated
you
with increasing velocity of electron in opposite direction. What
so
will be the nature of?
So you are approaching towards C. Suppose you have an electron approaching the speed of light. Suppose okay towards
Yes.
C. So 0.99, 0.98. So you will have the maximum values of resultant. But you will reducing the value. Suppose okay point 6, I say 0.8, 0.7, 0.6. So that corresponding values will also go on reducing. That's my inference from that. UX will be reducing resultant one. For this problem for this particular problem if the things is happening okay two electrons are ejecting in opposite directions okay and if you have a resultant formula you need to put it okay there if you have the resultant velocity I mean to say the relative velocity of the electron are lesser so correspondingly the velocity addition one also lesser comparable to the speed of light comparable to the get it
Yes, sir.
So please do this problem at home and also those peoples will send me a homework to that my email or you just upload on this assignment section also. I think those are the regular students who are regularly attending my lectures. I can only seize solution of those students only. Okay, those are not going to attend the classes and they are taking from somebody and answering that. I will take approach I mean to say I'll take their solutions will be later but you people are present over here so I will give you this assignment homework to you people only okay and please try to solve those and send it to me okay I will you can just see this I can upload this PPT on this class materials and see those questions okay on length contraction and this particular problem I took it from the book of Beiser on the twin paradox also you please solve those two problems and just send or upload on the assignment section otherwise on the chat files also you can upload the answers with the scan copies okay so this is for today. If you have certain questions, please ask me. Otherwise, I can stop today.
So,
बोला.
why are we using speed? I mean, is it speed or velocity?
Look at uh, so you always talking about the components. Okay, when we have vectorially, suppose when along the x direction, y direction, z direction, you want to calculate those values. Okay, you can say this is the velocity, resultant velocity or relativistic velocity you can calculate. But in general, if there is certain thing which is moving along a particular direction, you say, okay, you can ultimately say that the magnitude is the speed associated with that. Okay, so you are not worried about that vector component over there. Okay, so you can just find out the speed. Is it okay?
Okay, sir.
Sir,
Mhm.
if you pass some light in 2 dimension or xy plane in
Uh,
the 45-degree angle, and then we look toward the component along x-axis and component along y-axis, will
they
their
definitely,
value be also
yeah,
changed?
that will be a change. That definitely will be a change. We need to find out the resultant angular component also. Okay, with respect to the definitely along the x component, how's the change over there relatively given. Okay, so we need to find out. We need to write. We need to get it the first equation of that resultant value with respect to the angle. I think that equation has also been derived in the Beiser. I want to check that. If the angular component is mentioned. Is it your question? Is it your question or you have something?
I was asking for what will be their component.
You meant to say if there is angle is going to be changed, angular component is going to be changed, then what is the corresponding angular changes that you
Sir,
have?
given in kinematics, given if we are given speed, then
Mhm.
we calculate its component along x-axis and y-axis by v cos theta or v sin theta formula.
Correct.
And
Mhm.
I am asking that if I can we
Yeah.
calculate the component of light, speed of light along x-axis or along y-axis?
So don't say speed of light. Here I'm talking about whatever be the suppose certain things is comparable to the speed of light. Okay, certain things, and it has an angular component that we need to resolve. So we need to resolve those components. Okay, yeah. So you don't see speed of light. Okay, if you just see over there, it will always be a c. Okay, but you say something mentioned. Okay, there are certain things happening, certain body which has a velocity comparable to the speed of light, and that event is happening over there in the moving frame, then definitely okay, that will going to be a change with the angle also. I mean to say we need to take those components. Yes, correct.
बट सर असं म्हणतात ना रिलेटिव्हिटी मध्ये की तुम्ही लाईटची स्पीड कशीही मोजा ती 3 × 10⁸ भरेल.
हो, तुझा प्रश्न लाईट बद्दल ठीक आहे ना, मी लाईट बद्दल नाहीच म्हणतो. लाईट इज लाईटच आहे, लाईटची 3 येणारच आहे, ते काय बरोबरच आहे. पण हा जर तू लॉजिकली जर एखादा प्रॉब्लेम असा जर तुला दिला की इथे कुठेतरी एक बॉडी मूव्ह होत आहे आणि त्याचा comparable to the sea. Are you getting my questions? Over here it is like that. There are certain things, okay, moving in that moving frame. Okay, suppose electrons hai, and their value is, I mean to say, the perpendicular component say ki Vx prime. Horizontal component is Vx prime, but moving frame along the y is Vy prime over there, and along the perpendicular direction Vz prime. So how's the I mean to say that body is angularly positioned with respect to the moving frame. Accordingly, that the velocity component is also going to be a result. That's my thing. But C's remain same. That's your question. Your answer is correct, which is the true for the speed of light, whether whatever be the direction it is moving. For speed, it is no problem. I mean to say for light, it is no problem.
Sure. So do we have components of speed of light?
No, I mean to say when you are taking about the speed, okay, so it is a multi-direction. So how can you velocity? I'm talking about any things, okay, about other than the photon or other than the light, you say, okay, that has a component. That's what you have. So don't. So light as a light. Your questions don't. Your light will be definitely be a light. Your C will be a. Here in putting the values of C. Your value of C. You are ultimately getting a C over there. That's not been the things. But I'm talking about those components. Okay. Those are moving component and they have some other moving directions. Okay, if they are having angularly position or like that, okay, they definitely changes the velocity along that component. Okay, so that's what you say, na, speed has no, I mean to say light has no components. Okay, and however the other bodies other than the considerable bodies you can consider that has a component. So in general light has no component. Okay, that's what we have, the speed of light. Otherwise it's a velocity. Okay, hope I answer, so I can quit over here. I'll just end the meeting, or do you have more questions?
Sir, hello.
Bola, 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 bola.
What about C2?